All right, so this is the portfolio optimization project that took 2 weeks to put this together. And it was really to showcase a number of different points. One, some different authoring capabilities, such as the Ologs. So you can think of one capability that the Olog assistant will give is to express those invariants or conditions that must hold. And those are far more deterministic. And we use this as sort of a filtering phase. And I'll go into show you the detail of that. Then we're also showing off here some of the uncertainty. The uncertainty is going to come in terms of things like weather, for weather affects construction in certain regions. So we want to capture that. And the way all of that is expressed is through a Bayesian network. So we have a Bayesian assistant that helps with this. And then we're also showing the use of machine learning. And in particular, here we wanted to demonstrate authoring of a regression model as an example, built using Azure's ML Studio, and how we interface with that. And we also are interfacing with things like Power Automate and their common data model and common data services. And ultimately, this entire application is presented to its end user using a chatbot. So we just simply wanted to show how easy it is to integrate all of these different technologies into a single solution. We're focused on the Microsoft tech stack here, but it really doesn't need to be. It's just that they are a good partner for us, and this was a joint effort for the customer. So we start with a top-level problem question, and the problem question that we used to drive this project was, given a set of candidate projects and external factors, what should be the optimized portfolio? And we did this in such a way that you can ask this hypothetically. So we have a definition of what is in the portfolio. And so here it's a collection of project IDs. We oriented everything around net present value. So there's a per project net present value, as well as a global net present value or a total net present value. And we're also interested in maximizing the number of satisfied business goals. So this is more of an illustration of when we get to the optimization phase of this, it can have multiple objectives, and as well as a global optimization. In fact, we have a pretty sophisticated multidisciplinary optimization framework that we've built. You can see some of my tabs up here, global optimization, that include things like rig allocation, pipe tallying. So we're able to do constraint satisfaction, as well as the Bayesian networks, as well as using category theory to impose logical constraints on the domain. And so let's drill into that a little bit more. So we have a domain model here. So this consists of projects. So we have a paving project, software project, terminal expansion, large ship, small ship. And again, this is it's a small amount of data, but is illustrative of the overall problem solution approach. The projects have different kinds of goals. They have strategic value that they're going after, reducing costs, increasing revenue, ensuring safety, et cetera. These are aligned with different business goals that are represented by different business units, performed by different teams, which have people, et cetera. There are tasks over here. And just as a quick illustration, tasks are part of individual projects that were in the portfolio. And we use this as an illustration of, I can go over to, for instance, here's a Power App that might be part of your dynamics, et cetera. And I can, for instance, edit these things and just say Anglo. So this is using a Power App inside of Microsoft. And when this saves, it goes through a flow. So just to show how these things can be accessed by external services. So this goes and gets an authentication token from knowledge.mana.io, where we're hosting this. Then there's, this is not that interesting parsing, but the interesting thing here is this HTTP post. So when I updated this entry here, it's going through this flow. It triggers this flow and does an upsert back into our graph. And this is just an example of how easy it is to interface with external systems. So if I were to go back over here and click on the task, you can see here, task 99 has been updated to reflect the change. So in a Dynamics kind of environment or Office 365 environment, it's really nice to be able to have this kind of fluid integration across all the different systems. So going back over here, if I look at what are the main logic flow of how do I select and optimize the portfolio. There's two main tracks you can see in this function composition. The top one is really the business logic, and the bottom one is handling some of the hypotheticals. So you may note that these inputs are both optional. So I can run this whole thing, which I can do now. So I'm going to run this entire solution without specifying any inputs, and it'll give me the results of having run through all the logic and machine learning and Bayesian inference and so on. Without any inputs, it's using the entire portfolio, and that's what this is doing down below. So it'll pull the entire set of projects, and it'll look at all of the live factors. So this is actually using a real weather forecast. It's running a regression model, and this predict vessel cost by size. What this is doing is running a regression model that was authored over here. Like I showed you this earlier. So this was the training and everything, and it produces this model. That model is available at this endpoint here. So this is the REST endpoint in Azure that you hit in order to run the model. In fact, you can come over here to this consumption, and you see that they've provided you handily with some code. And you can just cut and paste this code back into our solution here. So this is the Lambda assistant. So you just cut and paste this, and now this function, when you invoke it with the input size, it will call out to this machine learning model that was developed in Machine Learning Studio, Azure Machine Learning Studio, and produce the results. So this is one of the things that's used in this overall solution. So if I go back, the first step that we want to do is, once we have selected the data that we're interested in, or use the overrides provided by the user, you can say use defaults when candidates not provided, is we have this function here, this curious function called check olog facts. Ologs are a category theory based approach for specifying these kinds of constraints, and we have an olog assistant here that has captured a model. And if I drill into this, you'll see this is effectively the gauntlet that imposes the set of constraints. And so given an input project, I expect to get that output project. You'll notice that the input is required, it's got the exclamation point, but the output is not required. So it could produce a null if it didn't meet the criteria. And it's a pretty simple criteria, and it was authored using this assistant. So I'll make this full screen here. And it's just this little graph, but effectively it's the primitives are these what are called types and aspects. So you can kind of read this as English. In fact, one of the main things you do, and so after you have made these relationships, and there's a very simple introduction and training that we do for subject matter experts. As I mentioned, that this is being used pretty extensively at a major oil and gas company, where we've trained their SMEs to express their problems using these artifacts. And this assistant will then generate all of the back-end code that's needed in order to actually make it operational. But one of the main things you do is you express facts as paths through this diagram. It's a very category theory thing to want to do, is make composition and paths through these things that must commute. So what this is saying is a project is run by a team, which is sponsored by a business unit. And that's this path here. So a project, if I give it an instance of a project, and then I, in effect, run the function, what is the team that runs this project? I get a team instance. And then I say, well, I run another function that is, who is that team sponsored by from a business unit perspective? And I get a business unit. So here I'll have an instance of a business unit that is associated with this project. The second path is starting with the project and ending at business unit goes this way. And it says a project has a goal, some set of goals here that align with business goals here that belong to this business unit. So if I put a project in and it follows both of these paths to produce the same business unit, then we know there's coherence in the underlying model. And this is one form of validation. There are obviously many things you can do with this, and it can get pretty sophisticated, but this is the basic idea of expressing these kinds of relationships and invariants in your model, which must hold in order for something to be considered valid or not. And that's exactly what this function graph is doing here. So there's the, given a project, it'll go through this path to get the team that is running that project, which is sponsored by a business unit. And then same thing with this path, which is the goals are aligned to the same goals of the business unit. And then there's a little comparison function, and this is automatically generated by this assistant. This also produces a domain model, which should mirror this structure here. So you have this kind of quad structure down here of project, team, business. So it looks like a little rectangle. So you have project, team, business unit. So it mirrors the exact shape, and you can see all the aspects in between. So this is, as I mentioned, using category theory under the covers. There's some pretty sophisticated capabilities that category theory provides, but we're trying to wrap it all in a very easy to use and friendly, SME-friendly interface for mere mortals to be able to express these things and not PhDs in mathematics. The last part of this is this constrained optimization. So you can see here that the technique we're using is to generate the candidate portfolios, computing portfolio MPV, and then maximizing that MPV. The interesting thing here is going to be in the marginal distribution calculated by this Bayesian model. So here is, it's a fairly simple Bayesian model. There are a couple of views here for specifying the priors, but you can see here the way we've mapped everything as ultimately we care about NPV. So this is our target, and it's influenced by project classes and project sizes, software success, and so on. And these are really just the bucketized probability distributions, priors. I like this view for experimenting. So you can run this model in forward direction and in backwards. So the backwards is called retrospection. So I could say that the project software success is certain and extreme weather is low. And you can see how this is dynamically updating the projected NPV. So it's nice. It's giving us this 50 million bucket, 100 million bucket. So it's a nice one with these distributions. I can clear these and I can run it, and you can see everything's dynamically updating. I can run it the other direction, say, well, I'm really looking for this bucket. And you saw that these changed, and these are your initial conditions that must hold in order for this to be the case optimally. So this is giving you a little feedback through some hypotheses, which is pretty cool. And again, this just spits out this marginal distribution. It spits out all the functions and provides all the updating that you need. So this is the updating of the network that can be used for example, the UI. Okay, so I ran this earlier manually inside of our authoring tool, but this is not really the way you're intended to consume this. This is not really where an end user will work. This is what you would get if you were to call this from an API surface. So we give you what were the external factors. This is 0.6 on extreme weather, 0.14 for project success. These are the per project NPVs. You can see that this one is probably the software project is thought to lose 40 million, but that's in the global optimization. You need to do this project or you won't get these values contributing to the net present value. Which is also a good illustration of why global optimization is important. If I were just to do local optimization, there's no way anybody would ever sign off on a software project that's likely to lose $40 million. But what we can show is evidence of, well, yes, that might be a losing project, but if you don't do it at all, you're not going to gain anything in these other projects. And again, this is sort of a toy, but it's illustrative of the concept. So what we ended up doing, just to illustrate another way of surfacing this data that wasn't just another web interface, was as a chatbot. So this is using an Azure chatbot that's making queries into the Q solution that I just showed you, much in the same way as the automate flow. So this is given a subset of projects optimized for NPV, get the subset of projects optimized for NPV given current conditions. So this is running the version where we don't override or provide any inputs for hypotheticals. So this looks very much like what we saw when I ran it inside the tool, which is the expected NPV is 135 million. But now I can also pose some hypotheticals. I can say the chances of the software project succeeding are 10%, and the likelihood of extreme weather at the project sites is 90%. And so now when I run this with my overrides, it'll calculate that the overall NPV is 88 million, and looks like there were more. Yeah, it doesn't want us to do up here. It still suggested that we can do the large ship construction project, but down here the large ship construction project has been omitted because it's not worth investing in. So this is, again, it was a 2-week effort to put all of this together to show all of the different points of integration, experiences and tools, and how a solution like this is architected in more or less a single workspace and then branches out into multiple other services.